the boundary integral equation in the case x star equal to x in the point k as belonging to S body. So this is x star, and this x star point is equal to sk point, and k is an integer number from 1 to m, and this point is a panel centroid. Okay, so essentially I am collocating the equation in a generic K panel. So what I have is phi, instead of write x star, I write phi k, the value of the unknown phi in the centroid K. Phi k, remember, this yellow line is phi k. This continuous line is phi in the x star point. Okay? You have this. You are able to distinguish this difference. Phi k is the discretized value, which is constant on a panel. Okay? And this is not a function of x, but it could be a function of time. Remember, we are studying a steady flow, please. And this is equal to, I am translating this equation, and therefore, in this case, E star is 1/2. So 1/2 phi k at the time t is equal to, now I have a surface integral which is a summation with an index m from 1 to capital M, and I'm actually performing this integral, this first integral here, A. And this A contribution note is A contribution, and is this quantity, this Greek letter is key, okay? Key like Christos, key. Key in the centroid M is a function, of course, is a function of time by a matrix element like BKM. And what is BKM? BKM is equal to the integral of G evaluated in the xk point, fixed, the old x star, and with x variable in ds, but this is the panel M, and we are summing in M. So we are considering this generic M panel, and I am summing all the contribution within this integral B, because in this integral B you have to perform the integral, over the body surface. So you have to sum the contribution of the panel plus the contribution of the panel, the other panel. You have a summation. The summation is exactly the corresponding discretized quantity of the integral. But you have supposed that the phi on the n is constant in the panel, and so you put this quantity out of the integral, and out of the integral, and name this like k key. So key m, yeah, this here is v body dot n evaluated at x equal to xm centroid here. So you have also discretized the boundary condition. You have to know the body velocity in all the centroid points in any time. You have to know the motion of the body, but not in continuous way, but in discretized way. You have to know the motion in each panel. This quantity is also known as normal wash. Normal wash, the impermeability condition. Somebody says downwash. Ever seen downwash? Yes. It's down when you have the wing approximated that like a surface, and you have only this as normal. The normal is coincident with the vertical, and so you have the downwash. But if you have a body, you have a normal wash. If you have a thick body, not reduce it to a surface, but a body, you have a normal wash. Okay? So this is also known as normal wash. Okay. So I have discretized A. Now I want to discretize B. Other term here, this term here, B. We have phi and dg on the end with a minus sign, look. And therefore, we have to perform this integral, and dg on the end is a quantity depending on x and x star. But phi depends only on x and is assumed to be constant in a panel. So you have a value of phi in the panel, in each panel. And therefore, this integral is again approximated like a summation. For again m from 1 to capital M. We have the unknown. Look, the unknown is here, but the unknown is also here. This is because of the nature of the boundary equation. Okay? So you have again the unknown here, and the unknown here is sum on m, it's a function of t, multiplied by other coefficient c, k, m. And again, c, k, m are another set of coefficients, k, m, equal to the integral on the panel surface m of minus dg in the n as a function of xk, fixed. And so this panel is the kth panel, excuse me, the m panel. So the index m is indicating the panel we're integrating. The index k is indicating the x star value. Okay, so we have xk comma x in the S. And so but these coefficients are fixed and evaluated one time. Stop. So we have B, we have C, and at the end we have also other set of coefficients for this part C. In this part C, we assume that delta phi is an unknown, but it's constant in the wake panel, because here I have an integral to be performed on the wake surface. And so, for this panel, this generic N panel for N running from 1 to capital N, capital N panels, we have to consider a summation from n, like Naples, from 1 to capital N, of delta phi, n, like Naples. This delta phi is a function of time, and this delta phi is multiplied by another coefficient like f, function of k and n. Okay, and this fkn is a coefficient similar to c, because here I have to integrate the g and the n again. Look, I have this minus sign to be included. I have included this minus sign in the integral definition and the integral definition. And so I have to define this new coefficient, the g on the n, on the weight. I am defining f like f k n, like Naples, and this equal to minus the integral on the surface n of the wake, this here, minus dg, no, too much, too many minus sign, minus, only one minus, dg on the n, evaluated at xk and x variable of integration in the x, in the s. This s is a function of x. Now, this coefficient fkm, ckm, fkm can be evaluated one time only, because these integrals are not essentially time dependent. In the sense, if the panel can be retained as as solid panel, rigid panel, without any kind of distortion. So the assumption that the panel is flexible does not affect the value of the integral at all. It's just like you have an integral on AB domain of a function. If you perturb the domain of integration A and B, small perturbation, the value of the integral does not change consistently. And therefore, we assume that the domain of integration of this integral coefficient is not varying in time. And so, we assume that the coefficient is not depending in time here. Time, not. Okay? The only dependency on time is on key quantity and free quantity. And so we have just an algebraic problem in any time. We have to solve an algebraic problem time by time. Okay? And look at what we have obtained. We have this integral equation equal to this, this, and this. How can we use this equation? Consider that we can also obtain parallelly an expression for the velocity in the field. Do you remember this? This formula? For the velocity, we could discretize also the velocity in a field. Correspondingly, we can divide our panel in our body in panel, and then we can evaluate, for example, let me write here this discretized addition for the velocity. We can represent the velocity v, vector velocity, in a point P. P is a point in the field, is not, is an index, is a point in the field. And this dp, as a function of time, is equal to, we can discretize directly this quantity, and we may obtain again a summation m from 1 to capital M of, again, this is the normal wash, so key, again, the same normal wash as before. But now we have to refer this normal wash to this matrix coefficient, which can be defined like a B vector PM coefficient as a function, not function of time. I will write you later the expression of this coefficient, but it's very easy. You have to just discretize this. B is the discretization of this. Plus, we have summation of, again, m from 1 to m of phi m. M is actually numbering the panel. Phi is a function of time. By another set of coefficient, vector coefficient like c, again, function of p, but function of the actual value of m. P now is the same of x star, and the index m is the x variable. And finally, for the wake contribution, we have again a summation for n from 1 to capital N, and we have this other, you have a delta phi n, function of time, multiplied by this vector coefficient p n. And what about this b, this c, and this f? This c is the discretization of such a quantity and of such a quantity. No, this is not the Laplacian. This is the gradient star gradient. For f, including the sign. Okay, just an example, B PM should be the integral on the panel M, of the gradient of G. The gradient of G is a vector having this derivative with respect to x of G, derivative with respect to y of G, and derivative with respect to zeta of G. And you have to evaluate this quantity at xp, x equal to xp, and you have to integrate in ds of function of x. And you have a matrix of coefficient. The important message is that we have this instrument and we have this instrument for marching step by step in time. And now the question is how to use this discretizer. The question? We have a double use. One is nonlinear use, and the other one linear. Of course, in elasticity, we are interested in the linear one, but I want to show you also the nonlinear one. In the nonlinear approach, we honestly assume that the wave is free to be generated by the solution. And in fact, this approach is also known as free wave approach. The wave, which is a special part of my domain, the wave is formally and practically part of my solution. And I want to evaluate this wave step by step in a nonlinear time marching. Stop. The second approach is a linearized approach, typically used for the aircraft, and Within this linear approach, we have a time domain and a Laplace domain formulation of the problem. And finally, I have a transfer function. Okay? So, in the nonlinear approach, also known as free wake, we have the following. First, imagine to have a sudden start. Your aircraft is at rest at time 0, okay? No wake. And in this initial step, you have zero velocity in t minus equal to 0 minus, you have airflow equal to 0. In t equal to 0 plus, so you have a step. You have u infinite not equal to 0. So you have a sudden start. Okay? In this initial time, you have this integral equation without this term, without the wake term. You don't have the wake. So look at this equation. This equation is just an algebraic equation. At t equal to 0, you have 1/2 vector phi, vector in quote. Vector means phi1, phi2, phi m is not a physical vector. Is a fruit of discretization. As for this reason, I call it vector in quote. So 1/2 this vector is equal to B matrix as applied to key vector. Again, key is a time vector, and I am evaluating this at time equal to 0 in t0. T0 plus. Okay? U infinite, and so you have to evaluate the motion of the body. Please make a distinction between the airflow, U infinite, and the velocity of the body. Velocity of the body is the velocity of the body. And here you have key is equal to Q1, Q2, and so on up to Km. Okay, so this is equal to this plus, not plus, minus, plus C phi, and that's it, at time equal to 0, to the initial time, okay? And this quantity are at initial time. Look, this is just 1/2 identity matrix minus C applied to phi vector is equal to B vector applied to B matrix applied to key. And then you can evaluate your potential flow at initial time by inverting this matrix as applied to key to the initial time. Okay, so you have the first picture of your flow. You are evaluated phi around the body surface only. First step. Note that we have an identity matrix here because this quantity, phi k, can be written, this phi k can be written like Kronecker delta k m phi m, right? So this is the identity matrix applied to phi, and that's the reason I write this. Okay. In the first step, I have the potential flow of the body. Okay. Now I can evaluate the velocity everywhere. Look, I have the velocity. I have the velocity. I use key, I use phi. I have already evaluated phi in a time. So I have the velocity everywhere. And so, note that if I have correctly considered my geometry, if I have a symmetric, look at this distinctive situation. If you have a symmetric airfoil with zero angle of attack, and if you have a non-symmetric airfoil or a symmetric airfoil with an angle of attack like this, in the initial time, you should have a velocity potential here and here identical, if symmetric. If not symmetric, you should have something different here and here. So potentially, you have a generation of delta phi. You are able to generate a wake. So the first conclusion is very simple. If you have all symmetric in a flow, you have upper and down of the airfoil the same flow, and you are not able to generate a wake. Okay, it's very easy to realize. But now we are in the general case. In two steps, in the second step, I can evaluate V where? I would like to evaluate V just here and here in the trailing edge. I evaluate V at trailing edge and evaluate V wake as average between V1 plus V2 by 2. Okay, so you have the wake velocity here, 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 here. You have the wake velocity in the trailing edge. We have wake velocity at trailing edge at time t equal to 0. And so we can move the wake in the sense that the position of the wake at time t plus delta t should be equal to the position of the wake, which is at the trailing edge at initial time t, plus the velocity of the wake just evaluated by delta t. Okay, so we are able, time by time, after evaluating the velocity, to evaluate the panel position of the wake. And therefore, in time 3, we can move our delta phi in the first row of wake panel I've generated. Why can you do that? Because you know that, put a condition, there is a continuity of phi upper and down position, and this difference of velocity potential can be convected in the wake regularly without any trailing edge sink effect or source effect. You can smoothly convect this continuity in the wake, and so you can locate this delta phi in the first row of wake panel you are generating. So you have generated the geometry of the wake. With this formula, we are generating the geometry of the wake geometry. And in step 3, you can locate your delta phi on wake panel and assign this value to the wake panel. Okay. Reiterate this step in any time. In the next time, you have first to solve this equation, but here now you have delta phi that you have already generated before. The old value are influencing the present in another position, but in another position. And now you have finally considered also this condition here. And let me do a check mark now. Okay? I have used Kutta condition because I have moved delta phi on the body to the wake, Kutta condition, and fourth boundary condition, I'm assuming that this wake, this continuity delta phi, can be convected on the wake surface by means of the defined wake velocity as average up and down. And ladies and gentlemen, this is the nonlinear step-by-step funnel method for unsteady flow. If you assume a motion for the body, if you assume this key, right? If you assume this key as a given quantity, so if you assume a motion, by this method you are able to evaluate anytime the velocity potential on the body, time by time, and on the wake. Remember that with the velocity potential, you can evaluate the pressure by Bernoulli theorem as byproduct. And if you know the pressure, you know the force. If you know the force, you know the lift. If the body is rigid, you know your generalized force. If your body is flexible, you have to take the pressure distribution, and in any time you have to project the pressure distribution on your shape function anytime. So obtaining the generalized force. Okay? But now we are describing just a part of this couplet process, okay? So now I want to go to describe not the nonlinear, but the linear approach. The linear approach the wake is assumed to be planar. As generated by the trailing edge line translation. Translate. No vortex roll up. No vortex roll up. Okay? This is described by the free wake. So, ta-ta, ta-ta, ta-ta. This is a plane, and what happens in this case? In this case, we assume the following. We have the body, discretization, and we have the weight discretization, and we assume that the delta phi here, in the wake point, in a time, in this panel, and let me write, excuse me, let me write the trailing gauge line. This is the trailing gauge line, red line. And we assume that the value here is equal to the delta phi at the trailing gauge in the trailing gauge in previous time, like t minus tau. And this time delay tau is something related to this distance, the distance between this point, the trailing gauge. Now, an approximation of the linear approach is on evaluating this time delay as equal to tau is equal to u infinite divided by x, excuse me, the contrary. This time is evaluated to be equal to this distance, x, divided by u infinite, as x wake, from here to here. Why? This is a suitable position. In fact, remember that any kind of velocity are velocity in the air frame of reference, in the sense airport frame of reference. We are in the airport and the aircraft is flying. So when you take the gradient of the velocity potential, you obtain the fluid velocity with respect to this fixed frame of reference. It's not the velocity with respect to the flying body. Now, it's the fluid velocity with respect to airport frame of reference. Okay, so this is the case, for example, of the V-wake. V-wake is evaluated as absolute velocity. And this absolute velocity is equal to the relative velocity of the wake. Relative is with respect to the body. This is the body frame of reference. This is zeta body. This is x body. And this is zeta no body. Air frame of reference. Like, let me use the standard x, y, and zeta. And so we have x, zeta, y, typically in the right wing direction, y. This is the convention in aeroelasticity. And this is the x-axis in this direction. But this is the body frame of reference. Fixed to the body. And this is the air frame of reference. So the absolute value is equal to the relative value of the body frame of reference, and plus the velocity of the body frame of reference. Look, this is the velocity of body frame of reference, and this velocity in this reference is minus I u infinite, because the aircraft is moving in this way. Okay, and so this velocity is minus I unit vector in x-axis u infinite. What linear approach implies as hypothesis? In the linear approach, this absolute velocity of the wake is put to be 0. This means the following: you are seeing the aircraft, the wake is fixed in my frame of reference. The absolute velocity is fixed, and it's 0. The wake particle does not moving. I see the delta phi fixed in the sky. Delta phi, and the flight is gone. And therefore, the relative velocity is equal to the opposite value of the frame of reference. And therefore, this is the reason of this tau expression. Tau, the time, is the space in a time, is the distance of the wake panel with respect to the trailing gauge divided u infinite. Because we are assuming that the relative velocity of delta phi with respect, if I'm sitting on the trailing gauge and see what happens to delta phi, I see the delta phi moving in the wake with velocity u infinite. I'm moving u infinite, but in practice I see, and this is the approximation, an approximation of linear approach. Probably, if you see the delta phi in the absolute frame of reference, you should see something moving, but very small quantity with respect to infinite, u infinite. Okay, so tomorrow we will conclude this approach, so showing you how to obtain a linear operator, transforming the vector of the normal wash in the vector of the velocity potential. And this is the operator E2, a matrix E2, I call you Y2. E2 as a function of Laplace variable applied to the vector of key in the Laplace domain should give you the vector of the velocity potential, ladies and gentlemen. And this is my promise. But we have obtained this in a quite general form. Of course, this E2 operator depends on B coefficient, C coefficient, and that coefficient are depending on the shape of the wing, of the fuselage. We can represent fuselage. If you are generating contact discontinuity, you have F coefficient. But if you have a bolt body like a fuselage, you don't have a wake, so you don't have C term, you have only B term. Okay? Tomorrow we'll complete this framework. Okay? Thank you.